Okay, so thank you very much for the invitation and the privilege to speak. So I wanted to talk about a semantic graph engine that we've been developing at Pacific Northwest National Laboratory for about the last 3.5 years. As we all know, we have a big data problem, and in particularly, the data is no longer owner-produced, but rather gathered from a variety of sources, including the web. And so the data tends to be unstructured and extremely heterogeneous. So the fixed schemas that relational databases have been using for many decades, 30, 40 years, no longer really is appropriate as a medium in order to gather and store and then process this data. The schemas are rigid. It forces you into a table format with fixed columns and typed columns. And then as new data comes in, which you don't really own, so you don't really know what's going to come in, those columns tend to be inappropriate for the new data, and then you have to reformat everything and reorganize everything. And of course, that takes time to do. And I've got examples of why, if you're in this unstructured world, and you really don't know what the next piece of data is that you're going to get, graphs are really the right way to represent the data. There's been a flurry of work in the NoSQL database areas. These scale out fairly well. They typically use storage systems or large clusters in order to save the data. But they distribute the data over those components, and it makes selection very easy to do. You can do that in parallel at each of the sites, but it makes really finding complex connections and particularly complex joins difficult. If you look at sort of the exponential growth of the big unstructured data we expect, the structured data will continue to grow, but really the situation is that we really have to tackle this unstructured explosion that we expect over the next 4 or 5 years. So what we've developed at Pacific Northwest National Laboratory is a semantic graph engine. It's called GEMS. It's a flexible data model that supports structured as well as unstructured data in a single form. So we're able to support data that's represented as a graph. So that, as well as we have attributed edges and attributed vertices, so that if we do have structured attributes for the edges and the nodes, we can save that in a table format and then process that structured data using selects and join operations. This is an in-memory data store. So we use both the local memory at a node. We scale across clusters, so we're able to store data across the memories in remote nodes and hide the latencies using multithreading. And we can also use the flash memory devices on a node. So currently at PNNL, we're buying a machine with 32 nodes. Each node will have 720 gigabytes of main memory and a terabyte of flash. So on each node, we'll have close to 2 terabytes of memory and a total of about 64 terabytes in the system on which we will store the data and process it, hiding the latencies using multithreading. Because the data is stored as a graph, we want to use graph algorithms in order to process the data. So we don't do selects and joins. We don't take the data stored in triple column stores or in graphs and then squeeze it into tables in order to do a series of selects and joins. That saves us lots of memory, lots of computations. I'll give examples of that. And it's really the reason why we outperform current systems that are out there today. We run on commodity platforms. We can run on desktop, single node system, optimized using OpenMP model, and clusters in cloud systems using MPI. So we have no special system requirements, both on the hardware or the software side. All you need is a C++ compiler and MPI. So we're trying to solve that sort of area in that unstructured form there for GEMS. Okay, so why do we perform better than others? This is an unstructured problem, best represented as graphs. So we want to store this data as graphs. We don't want to take unstructured data and squeeze it into a table format. Once you have a graph data structure, you should use graph methods to process it. You should then convert that graph and unstructured data back into a table in order to do a series of select and join operations. We support a general parallel programming model. Multithreading allows us to do both thread level parallelism as well as task parallelism. We can spawn operations at remote nodes where the data lives. We've developed our own multi-threaded runtime system. So we've developed a thin layer which runs on Linux in order to do the threading. So we generate lots of threads, tens of thousands of threads per node. We store those in task queues. We context switch between those tasks. And we do heavy data aggregation in order to maximize the bandwidth of networks. We use standard languages. Currently our high-level sort of query language is Sparkle. We're developing a Sparkle to C++ compiler. We have a large quantity of C++ APIs, which you can program in if you prefer that. The Sparkle to C compiler is certainly fragile and developing, but the C++ APIs is typically where we program and do the query processing, and that performs very well. And again, we require no special system, either on the software or the hardware side. Okay, so why graphs? So the data is unstructured. So here's an example from email. You may get this email, and it says, Mary called her sister Sally to discuss buying her 6-year-old daughter a pony for Christmas. So there's sort of 6 facts there you can pull out of that email, easily represented sort of in the RDF or subject predicate object form. And if you want, you can sort of put that into a table where we have 3 rows and we have a number of columns, and you can see that some of that space is already wasted as there's no data in some of those columns, as that data is not represented in that email. We also don't really know whose child it is. Representing unknown data in a table format is difficult as well. But then the real problem is we get the next email, and that says Sally rented Joe's condo in Hawaii for a 2-week vacation, and she paid $1,600 of rent, or $1,200 of rent. And those columns simply don't exist at all in the table, right? So now when that email comes in, you sort of have to redo everything. And that's a problem, right? It takes time, it takes storage, and it takes a lot of shuffling of data. But if we represent this as a graph, it's all pretty simple, right? We have a series of nodes and edges in the graph. We can store that in a variety of ways. So we have a node for Mary, a node for Sally, Pony. The child can be a question mark or blank node in RDF. And we can attach edges representing the relationships between those nodes as represented in that email. And then when the second email comes in, we can just add some more nodes, attach them to the nodes that exist in the original graph. So now we have a node for Hawaii and Condo and Joe. It's all very easily extendable, and we haven't had to shuffle any of the data we had previously or really get into any problems with reorganizing things. We've added new nodes, we've added new relationships, and all that's very extendable in a graph format. Very difficult to do in tables. Okay, so now that we have a graph, let's see if we can process things in a natural way. So here's a problem from the insurance companies. They want to find out when you call in for a quote whether you're a good risk or a bad risk. So they have a table of names and addresses, and they want to find out whether you shared an address or people you shared 2 addresses with, and whether they're bad risks increases your insurance rates. So they might have a table of names and addresses. So they want to know who I've shared 2 or more addresses with. So they have to basically select out 2 tables. So they select out a table of my addresses for John and another table with everybody who's not John and their addresses. Now, there's a variety of ways to do this. You can use, of course, index tables, hash joins, and all that. But in the end, you end up having to somehow or other get those 2 tables. Then you do a join on those to get a set of names and address for people I've shared 1 address with. And then you do a self-join on that to get the names of people I've shared 2 addresses with. So it's a series of table operations, sort of more or less order n-ish in size. And in the end, we end up with lots of space. We've used a lot of space to represent those intermediate tables and values. And in the end, we get 2 or 3 answers, right? So we've gone through a lot of operations, used a lot of space to come out with 2 or 3 answers. So the way we do this is, of course, we would have a graph data structure, which I've represented here. And so we have a dictionary which maps strings to vertices or node IDs. So in an order 1 operation, I can jump to the node John and start a thread of execution there. And that thread simply runs a parallel for loop, which says for all out edges from this node John of type lived at, spawn a thread at the remote node. Okay, so I execute a parallel for loop, I get some concurrency there, and now I have 3 threads at the 3 addresses where I've lived. And each of those threads executes a for loop itself, which says for all in edges of this node of type lives at, spawn a thread at the remote node. So now I get more parallelism, which is good because I need parallelism to hide the latencies. And now I end up with threads at each of the people that I've shared an address with. And so the 2 threads that reach the Fred node there, they update a counter. So the count at Fred is 2. Only 1 thread has reached the Mary node, so the count there is 1. And the thread that spawned at that remote node, since the walk is over, right, the processing is over, says if the count is 2 or more, output this as a result. If the count is 1, then it's not a result and the name isn't outputted. So in 3 steps, with a lot of parallelism, I can answer that question. I haven't wasted any space in creating intermediate values. I simply created lots of parallel operations and threads. I have lots of cores. I can hide the latencies with the memory. So I save both time and space and compute power as well. So if you have a graph data structure, you really want to process queries as a graph. Okay. Okay, so graph algorithms can take advantage of conventional storage hierarchy. Can't take advantage, of conventional storage hierarchy. They tend not to have much locality. As you saw in that example there, I'm sort of skipping across the data space to go to remote nodes, which could be on remote processors. We do want to use main memory. It's faster. We really want to avoid the I/O bottleneck to disk. But memory is limited, so if we want to scale to large data sets, we have to, of course, expand the size of our clusters, which means adding processors across the network. And distributed data, of course, occurs long latencies. But for many of us, for the last 15, 16 years, we've been looking at using multithreading as a way to hide those latencies using the inherent parallelism in computations. The key to multithreading is to be able to generate hundreds of threads per core, so you have something to switch between when when the current executing thread does a long latency operation. As you saw in my example, we do that by simply having nested parallel loops, 1 for every statement in the query. And so in that example I showed previously, I had 3 nested loops, and that would generate, of course, parallelism. In most queries, you could have 6 or 7 nested loops, and so you just get sort of a nice explosion, or at least lots of available parallelism is there. And we assign, of course, hundreds of those threads or thousands of those threads to each core. That provides each core with a large collection of parallel work that it can do. As one of the threads, the executing thread does a long latency operation to put or get values across the network. We switch contexts and bring in one of the other threads. We can switch contexts within a couple dozen nanoseconds. And the way this works is that if I have this timeline on a core, I could have a thread or a loop which executes those red operations there with gaps in between them representing the time it takes for the memory or the data for that operation to arrive. But of course, if I have multiple threads assigned to that core for operations, I can switch to the green thread, and then I can switch to the orange thread, so I can fill in that processor's timeline with useful work, and it doesn't have to sit there and wait. So the key to multithreading is A, generate lots of threads. We can do that with this nested for loop procedure that we've done in order to execute the queries. And we have the task queues and the switching operations to switch quickly between those threads. So we can scale up, on single nodes, servers with flash, and then even to full cluster systems. We're currently running on 64 and 128 processor Linux systems at the laboratory. So this is a stack we've built. At the top level, we've got, as I say, the Sparkle C++ compiler. And then below that, we have two levels of software. One is the semantic graph library. That's where our data structures are. We have data structures for tables, graphs, dictionaries, and a large number of graph algorithms, including all the ones in Sparkle 1.1, as well as other graph algorithms like shortest path, page rank, connected components, and the like. And below that, we have this multi-threaded runtime system, GMT, that we've built customized for the graph operations that we're doing here. Okay, so some performance numbers. This is from the Berlin benchmark. So this is GEMS versus Urika. So this is on the 1 billion triples data set. So it requires about 4 terabytes of memory. And so we have a 4 terabyte 128 processor Urika at the lab. We use the Urika system there to run these. We did, it's a little difficult when comparing with the XMT on what a processor to processor is. So we simply used a Linux-based system with the same size memory. So this is a 4 terabyte Linux system that we ran this on. It only had 64 processors rather than the 128 that Urika had. And you can see that for most of the queries on the x86 system, we're beating Urika by a factor of about anywhere from 50% to about a factor of 6. If you look at the cost of the Linux system versus that of the Urika, the cost performance increases to 1 or 2 orders of magnitude. With comparison to Neo4j, here we again tried to be as fair as we could to Neo4j, so we ran a much smaller problem, 10 million triples that fit basically in a single system. Neo4j is sort of a single system. It uses disk. So we ran a much smaller problem so that we could fit the problem in the memory of the server so that Neo4j wouldn't be minimizing the number of disk operations that it would have to do. We also rebooted Neo4j for each of the queries to find the best mode. It has 2 modes that it can run in. So we rebooted the system in order to run the query for the mode at which it ran best. We also did cold cache and warm cache examples for Neo4j. For 2 of the queries 1 and 3 in warm cache, GEMS was about the same performance as Neo4j, but for the other, all the other queries, were a factor of about 3 to 7 times faster. Neo4j is sort of stuck on a single server system. We can expand the problem, as you saw, for 1 billion triples, and even we're running Berlin at I think the largest we've done is 50 billion, because we can expand over multiple processors. We're also a graph library, right? We have that graph library layer. We have the multi-threaded runtime systems. You can program directly to those, in which case we can run a variety of graph algorithms. Now, we're not a graph library. We don't want to be in competition with GraphLab or Spark, Graphx. We're a semantic graph engine. That's what we're developing for. But a lot of the workloads are complex. You have to do querying, and then you want to run graph algorithms usually on those results. And so there's a need in the analytic workload for not only the querying part, but also graph algorithms that run then on the results. And so we are supporting and do have support for a variety of graph algorithms. More are being added every day. And here you can see a comparison of the GEMS library for PageRank with GraphLab and Graphx, and we're about 4 to about 16 times faster than those 2 library systems that are out there on a Linux system with about a few dozen processors. Setup times, this is important. How long does it take you to ingest the data and then create the dictionaries and the graph data structures? So we have 2 forms. We can either come from sort of an ASCII triple file, so the typical RDF triples, And these are our build times to build the dictionary, to ingest the data, read the file, build the dictionary, build the graph, and then save a gzip file for if we want to then reload the dictionary and library later on. So, you know, on 16 processors, we're doing that at a billion triple file data set in about 1,000 seconds, and it scales fairly well across 64p. If we have the gzip file, we can save a lot of time. So we restore the triples, we restore the dictionary, and then we rebuild the graph, and the times improve somewhat, about 100 seconds in each case. And so if you're on the 64 processor system, you're basically reloading a billion node graph in about 4 minutes. We support two sort of novelties that other graph engines don't. One is property paths. So Sparkle 1.1 has this star and plus notation in order to follow a number of links in succession of a particular type. I've got an example there on the right from a DOE problem in which I started the data resource node, and then I want to follow the subclass type down to the actual resource. So the way the sort of the loops we generate are shown here. So here's, you know, the first step in the query, which is this loop 1, and there I'm basically following. If I find an in-edge of type subclass, I simply recursively call this loop 1 in order then to trace down from this node, you know, other paths, either subclass paths or finally a type path here. And so property paths, which are difficult to do in a number of other databases, and some don't support them at all, in our system is very easy because it just turns into a recursive call of the loop function that's executing that statement in the query. Another key thing that a lot of people want to do is, of course, there are attributed edges. So in many problem domains, relationships have attributes and nodes have attributes. And typically the solution is to starify them like this. Urika does this as well as other databases. So for every entry, they'll create a node, and then they'll pin out all the attributes on the nodes as other edges. That causes an explosion in memory. It also makes finding paths difficult because you know, if I want to look at a series of nodes that are connected by a particular protocol, I have to go from the flow to the protocol, and then back to the flow, and then back to something else. And so something that was a simple path now has become sort of a back and forth operation. So what we do is we still represent the unstructured data as a graph. So here I've got IP addresses and then the sends to. So this IP address has sent a number of messages to this IP address. Each of those are represented as a type link or edge in the graph. And then since you don't have too many attributes, too many predicates in a graph, you might have a few hundred, maybe even 1,000. We're representing those in a 64-bit word, so we have lots of space in that word to hang off an address to a table, and then that table stores all the structured dense data. And so this sends to relationship here is represented by this protocol, and then the size and the timestamp and everything like that. So all the structured data, all the attributed data for an edge is stored in a table. Makes it easy now for me to do relational operations on that table on the structured data. It also makes it very easy for me to follow paths in the graph that I need to. So I get sort of the best of both worlds here with just a single indirection, which is stored with the predicate type. We can do the same thing for vertices. We don't have that quite implemented yet. But if a vertex has a particular subclass, then there will be an edge from that vertex to that class node, and off that edge, then we can hang the attributes for that vertex. So, for example, I'm a human being, so I would, the John node would have a link to humans, and off of that edge, then that type edge, which links me to the human class, I can hang off all the attributes for the John node. So I can use the same structure we have here for attributed edges to do attributed vertices as well. And I'm done. right on time. So what we've developed is a scalable in-memory triple store capable of knowledge discovery on web-sized data. As I said, we're running this on 64 and 128 node Linux system at the lab. We're running it on server systems as well as single nodes. It scales with data size. It has multiple programming entry points, so you can come in at the SQL level, you can come in at the C++ level. We compile the C code, so if you've already compiled the query, you simply run the binary code you have. We don't interpret, we actually run binary code. It's C++, so you can link in your statistics libraries, your math libraries, your other graph libraries, just like you would with any other C++ code. We are currently working with government agencies and early adopters. We have this installed at a number of our sites, about 4 or 5 of them. So it is available for use. We are a national lab. We don't produce products, so it is a prototype and sort of research quality. But we are seeking partners in order to transform at least what we've done to date into production. So thank you very much.
Thanks. Sort of an immediate question is there anything that you learned along the way? You've been at it a while that you didn't expect? Any surprises?
Well, I mean, look, I spent, since a long, long time at Terra and then at Cray. I went to PNNL basically to, work on the XMT project that was being funded by the DoD there. The ability to actually write a scalable, very thin, high-performance, software runtime system that, in some sense, does what the XMT does in hardware was a surprise, right? I mean, we were very skeptical of that. We actually had 3 projects, one which was looking at, sort of a redesign of the multi-threaded processor itself. We were looking at sort of a hybrid CPU multi-threaded accelerator with FPGA fabric in order to do the multi-threading operations. And then we had this sort of third project, which was originally funded at the University of Washington in order to do this runtime layer. And the guys at UW started showing some pretty good results, and so the other 2 projects sort of died, natural death, and that project resulted in a runtime system called Graphx. So we took sort of, what the UW guys had sort of done. We've modified it quite a bit and customized it for our library. So we don't do everything that Graphx does. We certainly don't do everything that the XMT does. But we do enough to support graph algorithms in the graph database. So that was certainly a surprise, but it has allowed us to scale, well on commodity cluster systems.
Other questions for John from the audience or the panel? Yep.
I didn't quite understand the GEMS versus Neo4j. You had a wonderful cache, but was it GEMS using Neo4j?
No. It's GEMS running the query, the Berlin queries, and Neo4j running the Berlin queries, right? So we used GEMS to execute the Berlin queries, the 6 of them. Okay. I mean, GEMS is a graph database, right? It executes Sparkle queries on RDF triple data.
Another question.
Hi, can you use SSDs to extend RAM?
Yeah, so that we expect to, right? So the system we've bought at PNNL has, as I said, 3/4 of a terabyte of main memory per node, and then it'll have 2 SSDs per node. So we'll have another terabyte of SSDs. We haven't had a machine to date where we've been able to, use SSDs. This machine will be our first machine with SSDs that we can then use. So we expect to take the global data structures, which are the graph, the dictionary, the composite result table, and things like that, and then spread that across the memory, both the main memory and the SSDs, right? And then, internally we will have the accounting mechanisms in order to know where data is in the global space, and then fetch appropriately. The SSDs are a little further away from the processors, so there'll be more latency to hide. But we can, so we won't be as fast as if everything was in main memory, of course, because there'll be more latency to hide. But we've got some preliminary experiments that show that with the multi-threading runtime system we've developed, we can hide some of the latencies, even the disk, and of course they're much, much further away, right? So we expect to get, let's say, reasonable performance coming off the SSDs, but it does allow us to then hold more in memory, avoiding the disks.
John will be around, I think, for a while. We're going to, in the interest of time, kind of...
Panel. Oh.
There's a question from the panel?
Yeah, I was wondering, is there a heuristic or algorithm that determines the subtree partitions?
The subtree partition.
Yeah, like if you have this one large graph and you need to
Right.
do this multi-threaded traversal across nodes,
Right.
what's determining what parts of the graph are where?
So the graph is simply spread equally across the nodes, right?
So every node has a distinct subtree.
Every node has a part of the graph, right? But it's simply spread across. The only thing that we do is we do sort of identify the nodes with lots of in edges, okay? And those we do sort of duplicate in local memory on the nodes. So that, and the reason for that is that if you have a lot of in edges, lots of things will probably be reaching you, okay? And so we make that sort of specialization. But that's the only partitioning we do. Otherwise, everything is simply spread linearly across the memory, and there's no partitioning or anything. And we hide the latencies with the multi-threading.